Okay, well, now let's use what we've learned to find a scaling law for heat transfer. Here, hang on. Okay, well, here's the situation. Imagine I fill up 2 cups of water, 2 cups with hot tea, a big cup here and a small cup here. And the question is, which one cools down first? All right? Well, you can probably guess the answer. And if you can't, then if you look at this quote by Feynman, it'll probably help you guess the answer. Remember this from Plenty of Room at the Bottom. But let's see if we can figure this out by using the variables and relationships that we just wrote down. Okay? We're going to idealize the situation that I've sketched here with this picture on the right. All right? Now we have a hot object, this pink sphere, which is in contact with a cold bath. All right? This might be a hot object in cold water. Okay? And we can describe this object with the following variables. The object is hot, so it's at some temperature TH. Alternately, we can say it contains a certain amount of excess heat energy, Q. All right? The hot object transfers heat to the environment, it cools, and the heat transfer in joules per second is PT. Okay? And heat is transferred from the hot object to the cool bath because the hot object is hotter. It has temperature TH and the bath has temperature TC. And so heat transfers and the object cools down. All right? And what we'd like to find is how the time for this process to occur depends on the size of the object or the characteristic dimension, D. Okay? So that's the problem we're going to look at. Okay, so first, just remember what we've established. We define these different variables: temperature, heat energy, heat capacity, and heat flow. And then we wrote down some relationships between these things. The first, called Fick's law, tells us how much heat flows when we have a temperature difference between two objects or two places in space. Okay? The power or the energy per second is given by minus thermal conductivity times the cross-sectional area times the change in temperature with respect to position. Okay? Secondly, we have an energy conservation. If power flows out of a hot object, then the temperature cools over time. The temperature changes with time, and delta Q delta T is equal to minus PT. All right, let's use that to analyze our situation here. Okay, so to start with, we said that delta Q delta T is given by minus thermal conductivity times, oh, I'm sorry, I wanted to write something else, to write this differently, is equal to minus PT, okay? Energy conservation. But PT is given by Fick's law here. So we can write that as minus um, the thermal conductivity times the area times the change in temperature with position. Okay? All right. Meanwhile, oh, well, okay. And so the rate of cooling you can see is proportional to the area, the area of our object, surface area of our object. On the other hand, delta Q can be written as the heat capacity times delta T. So if the temperature of an object changes by delta delta T, then the thermal energy in the object will change by delta Q. All right? But delta Q, sorry, but the heat capacity can be written as the specific heat times the mass. And the mass can be written as the density times the volume. And the important thing here is that this whole term is proportional to volume. The amount of heat stored in our object depends on its volume, but the rate at which heat is lost depends on its area. All right? Putting these together, we can see that on the left-hand side, we have specific heat times density times volume times delta temperature over delta time. And that's equal to, on the right, the thermal conductivity times the area times delta T over delta X. Okay? All right. This looks complicated, but we only really are trying to find the scaling law. So it's actually pretty simple. Here's the idea. Let's solve for the rate of change of the temperature. So this is the cooling rate, if you like. How fast does the temperature change with time? And we can write this as K times the thermal gradient divided by the the specific heat and the density and the area. Oh, sorry, I want to make this very clear what we're writing here. So give me just 1 second. Here we are. And the area in the numerator and in the denominator, the volume. Okay? That is to say that the cooling rate, delta temperature, delta time, is proportional to A over V. It's proportional to the surface to volume ratio, okay? And we know that the surface to volume ratio is proportional to 1 over the characteristic dimension. There, we've done it. We've found the scaling law for cooling. Okay? And what have we found? We found that the the smaller d is, then the larger one. In other words, the smaller the object is, the larger 1 over d is, and so the faster the cooling rate it will be. That is to say, and maybe to no one's surprise, small objects cool faster. All right? Okay. By the way, it's harder for mice to stay warm than elephants because mice are so small. They lose energy very quickly because their surface to volume ratio is so large compared to an elephant. Okay? In any event, that's what we found. And notice how because we focused on a scaling law, a lot of the details of the problem, all of this stuff, drops away. We don't really care about it at this point. All right, let's stop this video here.